got a mighty big subject here. First thing I want to do though, and at the dedication up there, they talked about the Albert Schweitzer room that was the first. And I want to help you to understand that, and I told Albert Schweitzer's family this. I knew his daughter. I went to California and met her back in 2005. And Ann Schweitzer's granddaughter that still tours the world giving piano concerts on Mozart, even though Johann Sebastian Bach was Albert Schweitzer's favorite composer. And he played Bach music incredibly so on the organ. But I personally believe, and I told Schweitzer's daughter and granddaughter this, that I felt like that Einstein and relativity may have inspired Albert Schweitzer's new vision of modern ethics and the ethic of Jesus, and bringing it into the modern world with modern knowledge. If you say that the ethic of Jesus was saying we need to care for everybody, we need to have reverence for everybody, we need to love everybody, and I grew up in a Christian household, and that's sort of the way I view things. And if you look at Schweitzer and his academic excellence, he was as good an academician as you could ever find. I mean, there have been a lot of really bright and brilliant people in history and that had incredible academic excellence all along the way, but Schweitzer was right there at the top. And anyway, when you factor in he felt like that if you took all of the ethics of history and you put them together, that the ethic of Jesus would sit on like a diamond on the top of the pyramid, and everything else would come beneath. But in 1915, exactly 10 years after Einstein in E equals mc squared, from 1905, Schweitzer, and I'd love to tell the story, but we don't have time, had the idea that went through his brain, Ehrfurcht vor dem Leben, reverence for all life. And I think he could see, because of relativity, the relatedness of all life. Now, Einstein related it to all things, but he did, in his ethical way, all life. And that's in a is encapsulated form in why I have such devotion to the man named Albert Schweitzer. And his moral genius, the literary genius of the greatest, probably the greatest American author, Mark Twain, and the genius in the world of understanding something that I grew up, and when I learned it in college, meant a lot to me. And that is the macrocosm versus the microcosm. We all can understand our own little world and the way we think, and it makes sense to us. But how is it that we're able to try and open our minds and understand the big picture? And does it get any bigger than the cosmos? I mean, Einstein to have, as a young person, and I don't know, he may have even, it may have been before his teenage years, he may have imagined at age 12 or 10 what it would be like to ride a beam of light. Whoa! And incidentally, what's the first thing you think of when you think of the countenance of Einstein? Am I not correct? Isn't that the first thing you think of? I did this. Drew this for the last couple of months just to do that. So it'll help you think of Einstein. Okay? Little story. This man takes his son to get his driver's license, and he goes in, aces the written test, takes his driver's test with the state trooper, gets his driver's license. They're motoring home. Son says, Dad, we need to make some arrangements here to so that I can know when I can use the car. And Dad says, well, there's some stipulations here, son. And he's, well, first of all, you've been getting C's in school, and that just doesn't cut it. I know you're capable of doing better. So you got to get a B average or better. Not only that, but you need to study the Bible more. And last but not least, you need to get a haircut. And so 6 weeks go by, and Dad gets an envelope in the mailbox that day, and it's from the school. And it's his son's report card. So he opens it up, and whoa, and he goes in, and he says, son, I expected you to turn that ship around, but you sure did it mighty fast. I'm impressed. This is real good. You got all B's and an A. And he said, and I couldn't help but notice that you've been studying the Bible every night, and but you still have not gotten a haircut. And his son says, well, Dad, you know, since you've had me studying the Bible more, I couldn't help but notice that Samson had long hair. Moses and Abraham, Isaac, they all had long hair. I think even Jesus had long hair. And Dad said, well now son, did you also notice that everywhere they went, they walked? I hope Dr. Varghese doesn't mind me telling the story. But Dr. Varghese got a letter in the mail from the World's Physics Symposium in Zurich. And they were wanting this eminent professor of physics to give lectures, and they're asking physics professors all over the world to go within 500 miles of where they teach and give various lectures. And so he said, well now, Joe Bus is not going to let me use the USA jet. Those are too short hops. So he says, I need to get me a limousine, but I need a driver. And somebody said, well, call Ross. He's got a good driving record. And so he calls me up, and I said, well, since it's for the university, I guess I can. So first day, we light out, and we go to this university, and he gives the lecture 2 or 3 times that day at different lectures. And I drive him around, and this goes on, and I had a little chauffeur's jacket and a cap, played the role, and that sort of thing. Well, into the second week, after Dr. Varghese giving the lecture, the same lecture over and over again, he said, Ross, you know, I've been giving this lecture, and you've heard it so many times over and over again, and I need a break here. Do you mind if I drive the car, and I'll put your cap and your jacket on, and you take my tie and put it on, and you give this lecture at the University of Tennessee? And I said, well, yeah, I think I could do that. So he gets in the driver's seat, and he drives me there, and I sit back there like, I'm an important professor of physics. And so we get there, and they meet us at the car, and they shake my hand, and we've got our biggest lecture hall, and it's filled to capacity, standing room only. There's even some newspaper and TV stations there. Your reputation precedes you, Dr. Varghese. I said, well, okay. So I go in, and I give the lecture flawlessly, and standing ovation at the end. And then when everybody quiets down and sits back down, the student stands up. And he says, well, Professor Varghese, if you have an extant star on the far side of the sun, and you discount Newtonian equations on gravity, and you look at the Banal coefficient of the imagined hypotenuse of the projection of the light waves going around the sun and the bending of the light, what would be the given relativity only and not special relativity, what would be that angle and what would be the Banal coefficient? And so I was just standing up there, and I looked at him, looked down at the floor, looked at the walls, looked at the ceiling, and I said, well, now, I'll tell you what. I thought this was an up-and-coming new Ivy League university. But I want you to know that I think that is one of the simplest questions I've ever been asked. I'm just going to have my chauffeur in the back answer that. Do you remember that? One last thing before I get deep into the subject here. I got a new student for the fall for Dr. Busta the other day. And he did reasonably well on his SATs, and he did reasonably well on the other achievement tests. And he wasn't the greatest student in the world, but he was very modern and up to date. And he wasn't quite the student that Dr. Busta thought he would want. But he did have some pictures, and I managed to get into Dr. Busta's office and get one of those pictures. And 50 years ago, this might would have been a little risque, but not today. Does that look like a new student? I think that's funny, yeah. And if Einstein were here and understood our culture, he would have laughed as well. Getting on track now as much as possible. I consider evolution the history of change. And if you'll notice in the Einstein room up there, I said, could the E also mean eternity or everything? And actually, from my vantage point, the best E would be evolution. And, but I didn't want to put evolution up there because it turns off too many people. But hopefully, in the next 40-some minutes, or 30-something minutes, you will see that from my vantage point, that mass times the speed of light squared, you're talking about changing mass and changing the speed of light squared to pure, unadulterated energy. Now, first law of thermodynamics. If you look at particles, one of the things that Einstein helped us to understand, in other words, the subatomic structure, considering protons, neutrons, electrons, that sort of thing. The first law of thermodynamics says you cannot destroy matter or energy. You only change. Now, if you change and cannot destroy it, logic says, if we had somebody from the philosophy department here, if it cannot be destroyed, it could never have been created. It is eternal. Now, we are, everything physical is made up of subatomic particles. And if it could never have been created, now we have a tendency to go back in time to the Big Bang. And if we go back to the Big Bang, and like I think it was in 1951, there was many of the physics professors of the world were called to Rome, and they had an audience with the Pope. And the Pope says, okay, right there you find God, and that is the beginning, and so on. Now, if you consider, and most of what I'm going to have to say comes from two books. Brief History of Time by Stephen Hawking. Wonderful book. And then a follow-up book, 13 years later, The Universe in a Nutshell. And both very powerful books, and Stephen Hawking will tell you, one of the things that he was trying to do, his goal was to take the world of physics, which is in, and I cannot say enough positive about the understanding of physics and physics professors. I personally consider it incredibly complex, and anybody that devotes their life to physics, I see them as a genius, period. I'm trying to understand this in the terms of the man on the street, which I think I am. And that's what Stephen Hawking tried to do here, and he will tell you this. And that's maybe the primary reason it sold 10 million copies. Went into, I think it's 20th printing in less than 2 years. And it's a staggering tome. And you can, if you start reading, 13 years later, he brings out things in here that he corrects himself from what he wrote in his first book, because knowledge is still expanding and is going to go on for a long time to come. And he talks about finding all of the ultimate knowledge that we can come across in the macrocosm. One of the things that Stephen Hawking said, and, well, incidentally, let me tackle Einstein here just for a second. Einstein, when he first came out with E equals mc squared, he thought the universe was static, and that it had always been and will always be. I don't know very many people in the world of physics today that would agree with that, especially considering the application of the first law of thermodynamics that I just mentioned. It stands to reason that if you cannot destroy anything, it could not have been created. So that has been crossed out. Now, after Einstein, well, wait a second. Let me tell you this little story. Einstein came to the United States in 1931 to attend a conference out in Pasadena, what's now in the Hale Observatory, but I think it was called the Mount Wilson Observatory back then in 1931. And there was a Belgian professor, and Einstein was attending the lecture. And this Belgian professor, Abbé Georges Lamartre, I don't know, some of the professors here may know this. But anyway, he gave a speech to all of these physicists out here, outlining the Big Bang. And during that speech, towards the end, Einstein stands up and starts clapping. That's it. That is the beginning. You know, look at this. And that was in 31. So the last, and incidentally, Einstein would have been considered a deist by any theologian in the first 2/3 of his life. But then, people that did not want to see value in Einstein and relativity, they began to try and demonize Albert Einstein. So what they did, they wanted to find God in his equation and they couldn't do it, so they tried to label him an atheist. And that was not true. But if you take, it did describe Einstein very well, but only from the classical evolutionary sense of the way the word got started, but not how it got to be demonized. A, as a prefix, means without. I mean, if you, in Biology 101, if you have an asexual protozoa, it's a protozoa that reproduces without sexual characteristics. Okay, so A means without. Theist means religion. Very early on, Einstein rejected his Hebrew religion. But he said also, a snail can shed its shell and still be a snail. I can shed my Hebrew theology and still be a Jew. And Einstein also, cute little anecdote of his, he said if relativity proves to be true, I will be known as a great German. If it proves to be false, I will be known as a wretched Jew. Those were his words. But anyway, and in the last third of his life, that would have been more applicable. But he used the word God basically like a deist. But the last third of his life, it came to mean less and less to him. And it would be hard, you would be hard-pressed to actually pin him down in the last third of his life. But anyway, Stephen Hawking made a big deal because he was the guy that, and he wasn't the first that came up with the idea of black holes in the universe. But he was the big promoter of saying, you know, it's just a matter of time, we're going to find them. And he got to see, and I think his doctoral thesis in physics, and I'd love for somebody to verify this for me someday because I've never come across it, but I think his doctoral thesis in physics was on black holes, but I don't know that. And a black hole is a collapsing star that has burned out all of its oxygen and it starts to cave in on itself, and the curvature of space-time around it creates such a gravitational field, and I want to discuss that in a minute, and it is so powerful as it's collapsing that as it collapses, it is so powerful that it will not even allow a beam of light or a wave of light to escape. It will bend that wave of light back into itself. Now, in his first book, Stephen Hawking got to see, I think in the late 70s, the first 3 black holes discovered in the universe. Now they're guesstimating that there's approximately 350 million black holes out there. Maybe we could get somebody here at the university to give an exact count of that. But anyway, now in his first book, A Brief History of Time, Stephen Hawking says that these black holes will be reduced down to the same thing that physicists call the Big Bang. It will be a singularity. Now, I wanted that in red. That is a big deal in the world of physics. Singularity, you can't separate anything. In fact, Stephen Hawking, in A Brief History of Time, says, well, I tell you what, when you get this black hole to reduce, keeps reducing down and caving in on itself, pulling everything in and in and in, it keeps getting smaller and smaller until you have a singularity. And I thought, that's it. That is it, because Stephen Hawking, when he talked about the Big Bang, he didn't go back and say that's where it began, because if you can't destroy anything, and all of these particles were in that singularity and it imploded on itself, where did it all come from? If it's infinite, if it is eternal. Okay? So, Hawking says, look at this, came from the cosmos. And look at our cosmos since the Big Bang, and let's just say this is where we are. Think about this, folks. I am absolutely overwhelmed at the brilliance of Stephen Hawking. When he was in high school, using a common telescope, and just looking, holding it in his hands and looking out into the universe. Oh, we don't have a static universe. There's red light coming from those farthest galaxies, and if there is red tint to those galaxies, that means they're further out because of the wavelength, and subsequently the universe is still expanding. We do not have a static universe. And they did this in high school with a handheld telescope. Do we have the makings of a modern day genius there? But anyway, now, so then, as you look at our vision since the Big Bang, then the universe is expanding and expanding and expanding. Well, let's just say we're right here at 14.7 billion years from the Big Bang. And they can measure this. They can look at the distance of these stars, calculate the speed of light, and go back to the focal point of where it began. We now know, there might be one or two people in this room old enough to remember when televisions had dials. And remember when you turned the dial, it would give that gray fuzz between channels? We now know that 3% or 3 to 4% of that disturbance between channels comes from shock waves from the Big Bang that are still reverberating through the universe. And anyway, so now if you come out here 14.7 billion years, and Stephen Hawking has estimated that we're about 200 million years from peaking the expansion of the universe. Now, if then it's going to start coming back together, and we're going to end up at the big crunch, when it's going to be reduced down to a singularity again. So, matter and energy are leapfrogging through the symbol for eternity. Particles cannot be destroyed. They have always been, and they will always be. And I was rather amazed, and by reading Brief History of Time, I thought, apparently erroneously so, that you would have all of these black holes, and the one that was the oldest and the biggest, the biggest bully out there, would keep gathering in these other black holes and everything that existed until you came down to the big crunch. And once you got down to the big crunch, it would keep coming in and pulling in and pulling in and pulling in until it could no longer pull in, and then it would implode on itself, and it would all start over again. So matter and energy are leapfrogging through eternity. And the only way that you can understand the evolution of infinity is to look at the flow. And if you follow this logic further, we have additionally validated the whole idea of creation. It has always been and will always be. Every particle in your body has always been and will always be. You and I won't, but those particles will. And it was Einstein and his E equals mc squared that discovered in these particles vast amounts of energy. And Stephen Hawking, when he was talking about all of this coming down and imploding, and incidentally, right here at the Big Bang, he said everything that we see, and incidentally, I can remember from Physics 101 in college and undergraduate school, the professor saying, if you take a basketball and you put it on the ground, and then you get a golf ball, and you get in your car and you drive a mile down the road and you set it on the ground, you're looking at the proportions of the particles inside of an atom. The basketball would represent the protons and neutrons. The golf ball would represent the electron, the negatively charged particle. And, aha, that's a lot of space. That is a lot of space. And so, if you go back, Stephen Hawking said that at this particular moment, and it wouldn't have been but a fraction of a second, hardly a nanosecond, everything that we see out here in the cosmos would be no bigger than the end of your thumb. And it would implode on itself, and it would start all over again. So when you look at the pressure in here, at one point, they estimated that the pressure inside the Big Bang, at the point of the Big Bang, would have been 10 to 20,000 tons per square inch. They have recalculated that, and now they're saying the pressure inside of that was 1 followed by 72 zeros, tons. That's a lot. Now, why am I mad at Stephen Hawking? Because he, in Brief History of Time, or when he's talking about the universe in a nutshell, I think he is trying to take us back to his first book where he's saying everything, I mean, the end of your thumb could fit inside a nutshell. This is a walnut. And that is mind-bending, mind-altering, staggering. But it's only been in the last, I think, 25 years that they now see that because of the laws of thermodynamics that you have the Big Bang and the Big Crunch, and this is the way, I mean, Stephen Hawking in A Brief History of Time gave 5 or 6 different theories on how this occurred. How we started out with a Big Bang supposedly, got to the Big Crunch, and a new Big Bang, and a new Big Crunch, and it's going on, and going on, and going on. Boy. And this is the symbol for infinity. It has always been, and will always be. In the world of physics, there is a term that they use a lot. And determinism is what creates, I mean, we were just talking about the first law of thermodynamics. If there is a singular exception to the law of thermodynamics, it is not a law. So when you're looking at the laws of physics, to either validate them, or you want to find the exception and come out with a new theory and look to science to have it either validated or eradicated, and come up with a new theory to explain it, etc. Because that's what science does. And that's what Einstein said at the end of his life. Einstein said that the only truly religious person was a scientist. Because, yeah, they may believe it, but then they're going to set out to prove it. The idea is to come up with a theory, but then you use science to prove it. The whole idea here of determinism, in 1827, there was a botanist by the name of Robert Brown. And Robert Brown was looking at the reproduction of plants, and he dropped some pollen in a glass or a petri dish or something, and particles started shooting out everywhere. And so what developed was what has come to be called the Brownian motion. And it is now, I think, evolved into what's called the uncertainty principle, which they want to use to modify determinism. That, yeah, you may have all of these laws of physics, but there may be the exception here. And if there is an exception, then we need to rethink our laws. Well, the uncertainty principle, my attitude is, and they have not come up with the equation or sets of equations, and incidentally today I hope you appreciate the fact that I have followed Stephen Hawking's position in A Brief History of Time, because Stephen Hawking was told when he was writing his first book, that for every equation that he put in the book, he would cut his readership in half. So he was trying to put these great ideas into terms, and I haven't come across anybody that has understood all of this. And if it seems like I'm trying to make you think I understand all of it, I don't. I think I understand maybe 70% or so, but there's a lot there that I don't understand. But in considering Brownian motion, considering the uncertainty principle and modifying the laws of physics in a deterministic way, my attitude is this: if we look at infinity, infinity past, infinity future, if there is no such thing as creation, if we're only discovering what has always been there, you know what? 1,000,000 years ago, was there the potential for understanding E equals mc squared? It was there. It was just discovered. Was the idea for television always there? We all know when it was discovered. But we, in the limitations, I think, of language, and the average person does not get the privilege of thinking like the physicists that are here, that get to think in mathematical terms that are more precise. I mean, you go back to Sir Isaac Newton. Principia de Mathematica, in which he talks about gravity. And I think he's been proven to be wrong. And we may get time to talk about that in the next 10 minutes. Determinism in the uncertainty principle, I think we simply have not discovered the theory that is going to produce the equations that can, in fact, predict the direction of these particles. It's there. We We just haven't discovered it yet. Just in the same way that Einstein discovered that the only way, and when I was young, I looked at mass times the speed of light, and you ended up with pure energy. But I never focused on the pure energy side, and especially from the standpoint of infinity. Einstein, he says in the Universe in a Nutshell that he was wrong here. That black holes do not reduce themselves down to a singularity. He was admitting he was wrong. So I thought, darn, I thought I was just beginning to understand that. And he's now apparently saying that these particles, as they're entering these black holes, that somehow the protons and neutrons are separated from the electrons, or these quarks, etc., and all of what we now call quantum physics and quantum mechanics. And in other words, now they're delving into the microcosm. And I think this is more complicated than this. But I'm agreeing with envy on just how smart these physicists are. But anyway, Hawking says, basically, that black holes just keep going and going until there's nothing left. And they keep, and he has discovered that around these black holes, if here's the lip, and it goes down like a funnel to a point down here, and around the lip is called what they call the event horizon. And you're beginning to get close to traveling at the speed of light, and the speed of light squared. But one of the additional things that they're apparently discovered in the last 20 years is that these particles somehow get separated as they're going in. And one reason why Star Trek was wrong when it had that guy that was going to go through a black hole. Once you're in there for a week or two, you're getting close to being nothing but pure energy. And you'd probably be no more than the size of a piece of spaghetti. And you would be traveling so fast. Can you add something to that? He's smiling, and I know he's a very bright man in the physics department, and if he can help y'all out to maybe correct some of my statements, I don't mind at all. I enjoy the thought. And anyway, but in the black hole, apparently now they see it as not going down to a singularity. And so I've got to revamp my thinking, and I don't quite know how to put it in, because after reading brief history, I saw the black hole as where you got down to the singularity, and that it was the singularity, so now there's something else that's got to create that singularity. Figure it out for yourself. Einstein, once he got, and he produced 5 essays in 1905. The first 2 had to do with molecules, and the last 3 had to do with relativity or relatedness. And everything is related. You and I are not only related, but we're related to all living things, like Albert Schweitzer saw once he understood relativity back in 1905 when he went into medical school to become a medical missionary, incidentally. And so Schweitzer could see the relatedness of all living things, and that's what he was concerned with. But actually, actually in the world of physics, not only are we related to all living things, but we are related to the earth and the universe. You and I, and every living thing, has minerals in it that it cannot live without. We are related to the earth. That's what the term relativity, and incidentally, the term relativity came into being, no, relative. The word relative came into being around 1500, about 500 years ago. And this is, it seems like a year ago, I looked in the OED and came up with these years, but I could be corrected on this. And the term relativity is less than 150 years, or right at 150 years old. So it's a new term. Now, but intellectuals were beginning to think about this because of the first law of thermodynamics back in the late 19th century. And there was a book written in 1855 by a German physicist by the name of Ludwig Buchner, simply titled Force and Matter. And very powerful work. You can download it off the internet. All you got to do is look up Ludwig Buchner and you'll find it. It's B-U-C-K-N-E-R, and I got the little umlaut over the U. And it's a staggering idea that the intellectuals were beginning to think in that era. And you can see the evolution as it came into today. The three essays that were called Relativity and the Photoelectric Effect is what helped Einstein to get his PhD in physics and get to become a professor, which in that day and time, anybody in the German world, the ultimate sign that you have arrived was to become a professor. If you had the word professor by your name, you had arrived. And it was relativity. Well, actually they gave him his PhD, his PhD for the photoelectric effect. But it's relativity that got everybody's attention. And they knew the ramifications psychologically and intellectually of relativity, and they wanted to maybe not give an additional validation to that, so they gave Einstein his PhD based on the photoelectric effect. Gravity. It seems as though, now in 1905, when his three essays on relativity, and it was called Special Relativity in 1905, it seems as though the world liked the idea. He was opening the doors to knowledge, and I mean, it made the 20th century one of the most incredible century in all of history. But then, he had some additional thoughts. So then, 10 years later, he had finished General Relativity in 1915, but he did not publish it until 1916. And that's where he apparently destroys that's apparently where he destroys the idea of Newtonian gravity. And I'm still trying to wrap my mind around this, and I'm just going to throw this out to you. This is the way I understand it at this point, and I need to know more before I would say this represents total insight into Einstein and general relativity. But it appears as though, and I think it was Neil deGrasse Tyson on Nova, but I could be corrected on that, and believe me, things on the internet and on television, I don't know that, I think they should all be taken with a grain of salt. But apparently, when Einstein in General Relativity in 1916 publishes his papers, he destroys the Newtonian notion that when that apple fell from the tree, that it was attracted by gravity, pulling it to the ground. That apparently is not the case. Apparently, there is different gravitation, what we would call gravitational pulls, which is not correct. And that's one reason why relativity has helped them to understand that there's going to be a different gravitational force on different planets and stars and that sort of thing because of their size. The bigger, you know, the greater the gravitational pull. But relativity apparently says, and if you folks quote me, please use that word, because I'm not saying it is this way, but it seems, from what little bit I know at this point, this way, that it is the curvature of time and space. And incidentally, you have no time if you have no space. You have no space if you have no time. And Einstein was saying that the curvature of time and space is pushing things, not an attractive force inside. Although both books of Stephen Hawking here, he uses the term attractive to describe gravity. That's one reason why I'm trying to be as humble as I know how here in relationship to this subject. But look at this marker. Am I pulling this marker towards me? Am I pulling this marker towards me? Now, I'm not holding on to it, but it's coming towards me. I'm pushing it. The end result is the same thing. So, if the apple goes to the ground, is there an attractive force inside, say, let's just say the electron force, or what have you, that's pulling it to the earth? Or is it the curvature of time and space that is over it that is pushing it? And one of the things that helped me to understand this, I think, and somebody like some of these professors could enlighten me, but if you think of a drop of water, say that we've got a leaky pipe and it's in the ceiling, and one drop comes down, and you see it forming there, and finally it drops, and it's round on the surface, but it's got a little tail on the end. Is it being pushed? Or is it being pulled? You would think if it was being pulled, it would have that point on the front, not on the back. I honestly don't know, but I'm asking a question. And I think it's a good one. Not like the physicist to tell me what I don't know. We wanted to have a question and answer time, and I have a lot more to say, but I think I've opened enough doors and question marks, hopefully. And I don't know that, if you were to ask a question, I don't know that I can answer it, but I'd try. Or I would defer it to some of the professors here. Any questions? Shoot.
Is determinism, is that the controlling factor of singularity?
They can determine physics that are involved there, and I don't know how many would be, but yes, I am also a psychological determinist. Simply, and I think it is our vanity that gives us what religion says is free will. If I was Dr. Where's Becky here? And if I was born, I had the same DNA and same genetics, same parents, same experiences in his childhood, same friends, same everything. I would not be like him. I would be him. Exactly. Same thing is true if you were me, or Dr. Wood, or anybody in this room or anywhere in the world. And so I'm a psychological determinist, and remember when I said that the uncertainty principle that evolved, I think, from the Brownian notion of motion, that the uncertainty principle seemed to modify in physics determinism. And I would say, I think it's just a matter of time before we discover the formula that can predict this random motion. So I'm a thoroughgoing determinist, physically and psychologically. But that is a very debatable subject. You understand what I'm saying? And I don't want to extract any dignity from the human race whatsoever.
Ross, I know that some of our Odyssey people here have a 1:30 class, is that right?
Yes.
To go to, but I also know that many people in the room probably have questions for you. So what I'd like to do is break right now, allow our Odyssey people to go to the Humanities building if they have a class. And those of you who would like to stay and ask questions of Ross, please feel free to stay. Sandwiches and drinks.
Thank you very much.
Let's thank I always tell Ross that he's the one man that makes me think, probably more than anyone else in life. And he has certainly done that for me today, and I hope he's done that for you. Thanks again.
Thank you. Thank you very much.
What do you think? Physics is a difficult concept for people.
Everything in mind.
Thank you.
Really is.
Did you ask a question yet? I've asked a lot.
I'm waiting till the end. I want to save all mine for the end.
Good. I'm letting it sink in.
I work on it. I think it's a good organization.